A few years ago, I had the amazing opportunity to visit Venezuela. It is an incredible country. It has its challenges, but it is the most beautiful place I have ever visited. The Caribbean coast, with its white sand, turquoise water, and blue sky, is an amazing place to be. But what really struck me is the heat from the sun. It is fierce. I needed to protect my skin from the sun, and well, I didn't. I got the worst sunburn ever. It took me days to recover, and I really should have known better. From an early age, we're being told to put on sun cream. But what makes the light from the sun, and more specifically the UV light, so dangerous for our skin? What happened at the molecular level that is so destructive? So grab a pair of shades, your sunblock, and let's dive in. This is Think 4. Light is a spectrum. It goes from the lower energy radio waves, microwave, infrared, and visible light that won't interact much with the structure of molecules. But past visible light, ultraviolet or UV, X-rays and gamma rays are known as ionizing radiation. This means that the particles of light, or photons, of these types of radiation can break bonds inside molecules. On unprotected skin, this bombardment can cause immediate sunburn. In the long term, UV light can damage our DNA, which has been linked to skin cancers. To prevent damaging the skin, a simple shield can be applied that we all know as sun cream, sunscreen, or sunblock. They will absorb or reflect the harmful UV light to prevent the catastrophic interaction between the high-energy photon and the molecules in our skin. So what exactly happens that is so dangerous? When a UV photon interacts with a covalent bond, it has enough energy to break the bond apart. This results in atoms that have one unpaired electron. This atom, called a free radical, is highly reactive and is going to wreak havoc on anything it touches. Because of their high reactivity, they often react to produce more free radicals, which leads to a chain reactions. These reactions follow a three-stage process. First step, initiation. The covalent bond is split in two by the UV photon, leaving each atom with an unpaired electron represented by a dot in this chemical reaction. Dividing one molecule leaves two highly reactive radicals. We might think that this horrible scenario could be stopped if we left the sunlight, but no. Once a reaction is initiated, it can continue without any source of UV, long after exposure. Second step, propagation. The now extremely reactive radicals formed in step 1 can start their carnage. These free radicals will be able to pull atoms off from their stable molecules in a desperate attempt to recreate that stable covalent bond. In the process, a new free radical is being produced, which can in turn react with another molecule, which becomes a free radical instead. And then another, and then another, and then another, until third step, termination. This destructive chain reaction can only stop if a reaction occurs where no other free radical is produced. This can happen if two free radicals react with each other to combine their unpaired electrons to reform a covalent bond. Once all the free radicals have combined to form stable covalent bonds and stable molecules, the reaction will stop. This is known as termination. On that paradise Caribbean beach, I had no idea what fierce chemical reactions were happening right there on my skin. But I was painfully reminded that evening, and the day after, and the day after, and the day after. So next time you're out enjoying a beautiful sunny day, don't make the same mistake. Put on your best pair of sunglasses and a good layer of sun cream, because now you know. This was Think 4. Thanks for watching.